Hi everyone, in this video I'm taking a look at a multiple choice question which asks us which of the following integrals has the largest value, and then we're given these four options. They all involve an integral between the bounds of 0 and pi on 4, and we've kind of got various, I guess you could call them variations of tan x. So we've got tan x dx, tan squared x dx, 1 minus tan x dx, and then 1 minus tan squared x dx. And the student who sent this through particularly asked whether there's a way to think about this question that doesn't require you to just go through and evaluate every integral. And I think that's a good way to frame the question, because I think in the context of doing something like this on an exam, it might take quite a bit of time to do all these integrals, and if there's a way that you could save a bit of time, that would be helpful in the context of an exam. So my instinct here was to think about using charting and how that might be helpful. But what I might do is I'll put a little pause in the video, and then you can have a little bit of think about how you might tackle this using charting, or even if there's another way you could think of. Have a bit of a think, and then we'll come back and I'll talk through how I'll go about this. Alright, so here I've just written up the four options we're trying to pick between. We're looking for the integral with the greatest value, and I've drawn up a few axes here just to help with the approach I'm going to take, which involves charts. Now, before I kind of worked out this solution, I reached out to a few of my university math teacher colleagues to see whether they had any other ideas apart from charting. The consensus seemed to be that thinking about this with charts was probably the way to go. In particular, I should give a shout out to Simon Crawley, who really went to quite a bit of detail thinking about this. So thanks for the help, Simon. And Simon actually does a lot of tutoring, I think in person and online, given COVID these days. So if you are looking for a good math tutor, I'd recommend Simon. He definitely knows his stuff, and he knows he's a very good teacher. So what I might do, I'll give a link to his website so that if you are looking for a bit more personalized tutoring, maybe you could think of him as an option. But now coming to look at how we can think about this. So I think there is a way to kind of do this comparison without having to do a single integration. And I think it all comes down to remembering that the integral of a certain curve between 2 points is essentially the area under the curve. And I actually think we can get away with not only not integrating, but we don't even really have to chart all of these options. I think if we just chart a few of them, we'll get to see, almost using just logic, which must be bigger and smaller, and then be able to work out the correct option. And what I might do is I'll start by charting up the simplest one, tan x, because hopefully if you're kind of dealing with calculus questions like this, hopefully you're quite familiar with the tan x curve. I think it's easy enough to draw, but if you wanted to, you could kind of pick out a few key points. For us, obviously a key point is 0, because 0 is the bottom of the integrand. So if I did tan 0, what do I get? I get 0. Hopefully that's no surprise. And then if I did pi on 4, so if I just did 180 divided by 4, that's 45. Hopefully you don't even need to plug this into the calculator, but if we do tan 45, you'll see that's 1. That's from that quite well-known triangle, right-angled triangle. So here I'll just plot 1. And essentially, I might not draw this perfectly, but the tan curve kind of follows this shape. And it kind of inverts, and it keeps going beyond here, but we're really only concerned with the bounds of the integral from 0 up to pi on 4. And so given we know that at pi on 4 the curve is 1, we know that we're kind of thinking about these bounds here. And as I mentioned, to integrate it would just be to think about the area under the curve within the bounds. So what I've just shaded here, you could think about that area as representing option A. So we've kind of evaluated option A visually without actually doing the integration. Now what we can do is we can think about option C, which is 1 minus tan x within the same bounds. And kind of visually you can see that 1 minus tan x, if I wanted to plot it, I actually won't plot it, but if I wanted to, it would be 1 minus 0 is 1, and then 1 minus this small number is a big number, and so on. And you kind of would end up with the curve just kind of inverting, and then you get the area under it. But rather than actually draw that up, I can kind of know just logically that the area under this curve, or the value of the integral, is essentially this area here that I'm shading in red. So kind of right away, we've now evaluated visually at least A and C, and you can kind of see just by visually inspecting that this red area here, which is C, it's bigger than area A. You can kind of see that visually, and if you thought about it long enough, you'd kind of see, well, you're taking 1 away from all these fractions, so you should end up, when you add them all up, with a bigger result. So already I know that the answer can't be A, because I'm looking for the greatest value, and I know C is greater than A. So I've kind of cut out one option right away. Now we've got to think about what we've got left. Now, you could, if you were doing this quickly and roughly in an exam, draw everything on the one axis, but I've drawn up 2 axes just so that things don't get too cluttered. And what I want to do now is focus on the tan squared options. So tan squared x, 1 minus tan squared x. And what I might do, just lightly, I might just put these bounds onto this axis too to help with our comparison. And I'm just going to kind of try and lightly replicate this tan x curve just as a dashed line, just for comparison, because if we think now about the tan squared x, if we're dealing with all these values that we know are fractions in terms of tan x, well, if we were to square it, when you square a fraction, you'll always end up with a smaller fraction. So for example, if I was to say take a half and square it, I get 0.25, which is smaller than a half. And that's going to be true for all fractions. And so even without technically plotting, I know 0 squared is still 0, and I know 1 squared is still 1, so my curve is going to start and end between 0 and 1, but actually the tan squared curve is always just going to be lower than the tan x curve. And so, again, without actually doing all the mechanics of it and then taking all that time, just with a bit of logic, you can think, okay, well, I'm going to have a lower curve, so this shaded area would be the integral of in this case, tan squared x. So what I've just shaded here is B. That's option B there. And right away, I can see that B is going to be less than what we had as A, because the curve is lower at pretty much every point, apart from the start and end. So I can say B is less than A. So right away, I could strike out B as not being an option. So I've kind of reduced this now to again, a coin toss. If I was just to guess between these two, I'd have a 50-50 chance, but I don't think we need to guess. We can just keep doing a bit more logical thinking, because again, now I'm doing 1 minus tan squared x, and I can use similar rationale to say, well, that must be what I'm shading here in red, being what's left in this rectangle, basically 1 minus at every point. If I was to draw that up and then shade under, I've effectively reflected it, but I don't need to worry about doing that. I can just know that this is the area. So this would be the area of D. And we can see that D, just visually inspecting, must be greater than C, because we've got this line at 1 which stays the same, but what's left over from this tan squared x curve is more than what's left over from this tan x curve. So the bit left over that I've just shaded as D must be bigger than the bit that was left over here. So by the power of deduction, we can strike out C and say that the answer to this question must be D. Panic boom! So there you have a way to think about this integration question without actually doing any integration at all. It really just came down to thinking logically and making use of the knowledge that the integral of a function is the area under that function's curve. And so with a few little quick, simple sketches, you'll be able to work this question out, and hopefully you'd find that that would be quicker in the context of an exam than actually working through all of these integrals. And maybe in terms of exam taking strategy, what you might do is you'd use this approach to kind of work out the answer, continue on with the exam, and hopefully you get through the exam with enough time to check your work. And a nice way to then check this, if you had the time, would be to go and actually do the integrals and confirm that this approach gets you the same answer. That would be a very, I think, robust thing to do. It would be a smart thing to do in terms of trying to make sure you haven't made a mistake anywhere. But hopefully you found that explanation helpful, and tick boom.